Hi, everyone. Thank you so much for joining us today. My name is Mia Burke, and I am Program Manager with Hanford Challenge. Hanford Challenge is a nonprofit based in Seattle that focuses on cleanup of the Hanford nuclear site and works closely with whistleblowers, workers, and insiders who have issues that are not being addressed. This is the 12th webinar of our Nuclear Waste Scholar Series. We've made it to our 1-year anniversary of the series, and we're so grateful for all your interest and support. We started the series to inspire action and involvement with Hanford Cleanup by inviting movers, shakers, and thinkers to share groundbreaking scholarship, art, research, and experience working with nuclear waste. It is my pleasure to introduce our speaker, Joshua McGuffie. Joshua is a doctoral candidate in the Department of History at UCLA. His research focuses on the intersections between biology, medicine, race, and the environment during the U.S. atomic project. Joshua earned a master's degree from Oregon State University, where he studied ecologists working at Hanford's Arid Lands Ecology Reserve. Along with his academic career, Joshua serves as a parish pastor in the Evangelical Lutheran Church in America. Just as a heads up, Joshua's presentation will be about an hour long, and we will leave time after the presentation for Q&A. If you can't stick around for the whole time, feel free to leave. We will be recording the presentation, and we'll share a link of the recording with everyone that registered. Thank you so much for joining us today, Josh. I'll pass it to you to talk about your work.
Thanks so much for the great introduction, Mia. I appreciate it. I'll do what all people do on Zoom now, which is just take a moment to share my screen. And so hopefully now everyone can see the first slide. So as Mia said, my name is Josh McGuffie, and I'm finishing my PhD in the history department at UCLA. I'm an historian of science and the environment, and as she pointed out, I did my master's degree on ecologists who worked at the Arid Land Ecology Reserve. And so this is actually where the genesis of this talk that you'll hear today came from, because I researched ecologists who worked in the 60s and 70s at Hanford. As I went through their archives and read letters that they sent to each other in reports, I saw a bigger story. And that bigger story had roots at Hanford that went all the way back to World War II. So it's these roots, the foundation of biology and the biological sciences at Hanford, that I ended up researching for my PhD at UCLA, which I'm happy to say I just submitted to my department. So for those of you who've gone through academia or had family members silly enough to go through academia, this is an amazing thing. So if I'm happy, that's why. This is the story that I'd like to share with you today about how an unlikely alliance of fisheries biologists and medical doctors contributed to Hanford's scientific DNA during World War II and the first years of the Cold War. Though before we get into this history, into this bigger story, I'd like to walk you through some biology and through some terribly rudimentary physics, because I am not a physicist in any way, shape, or form, and also through some World War II Manhattan Project geography. So let's take a look at biology first. We're going to meet some hot fish today. And by hot fish, I mean fish irradiated, exposed to all manners of radiation. This is the first hot fish that we'll see. And if you take anything away from this lecture, if you take one thing with you, I hope that it's you have now seen a Chinook salmon in a straitjacket. And if you can see my pointer up here, this is what the biologists during World War II referred to as the straitjacket. You can see that the scientist is kneeling in a pond and has removed the salmon from the pond in order to place it in this immobilizing device. Why? you may ask? To answer this question, I'd love to zoom in on what my main argument is today, what I'm trying to sell you on, the big point of this lecture. And that's all about putting fish to work in order to create useful data about the biological effects of radiation. There are two threads that I kind of want to weave through the talk today, and we'll keep coming back to them. So here they are. The first is that salmon exposed to radiation in the lab, that these salmon are able to produce data about fish and other animals, including human beings, out in real environments. So fish exposed to radiation in the lab can teach us about all manner of animals exposed to radiation and entire populations of animals exposed to radiation out in nature. The second thread that weaves through, that ties the story together, that weaves through the whole thing, is that salmon data in the early years of the Manhattan Project really encouraged an idea that there was a threshold of safety, so that exposure below a certain level of radiation could either be safe or at the very least statistically benign. These are our two big ideas. Salmon can produce data about other animals and people, and that there's a level of radiation exposure below which there are really limited consequences. Now, these two threads required that hot salmon and hot steelhead trout become data production machines during the 1940s and 50s. And in the hands of the biologists who we'll meet, they did. The fish produced three distinct types of data. First, they produced population data. So data about how many irradiated fish died, how many irradiated fish were deformed, and in what ways. Collecting this data involved counting tens of thousands of irradiated baby salmon at two labs in Washington State, which again, we'll get to, trust me, the history's coming. So there's population data, but there's also somatic data, or data about the body. Collecting this kind of data involved taking tissue and organ samples and looking at them under the microscope. There's a third type of data, and that data has to do with radiation meters. So think about Geiger meters or scintillation tubes if you know anything about measuring radiation. Collecting this data involved taking tissue and organ samples and using a meter in order to take account of that sample. The fish that you see in the straitjacket is being immobilized because the biologist in the picture is about to use a scalpel-like device to take a tissue sample in order that that tissue sample can go back into the lab and be looked at under a microscope in order to create this body data. The biologist literally counted the blemishes on very, very small samples of organ and tissue samples in order to see how much effect radiation had on a fish. Okay, so that's a super quick run through some biology, and I hope you can hold it in your head because now we need to do some physics. So salmon and steelhead trout collected from Washington State hatcheries, and in particular in this story, really from the Sue's Creek hatchery south of Seattle, they became data producing machines in this story because they were exposed to radiation. Radiation transformed them so that they could give biologists the kind of data that they wanted in order to anticipate other radiological problems that would occur at the dawn of the atomic age. I know that I fall into the trap of just using a lot of shorthand when I talk about radiation. So I thought it might be helpful to just go through three important types of radiation that are useful for our story at Hanford and for our broader Manhattan Project story. So let's zoom in. The first type of radiation that we'll look at are X-rays. And you see that, and we're reminded that X-rays are simply on the electromagnetic spectrum. They're waves. Again, I'm not a physicist, so I don't want to deal with how light is both a wave and a particle. That's too much. But for what we need to think about today, X-rays are simply high energy waves that since they were discovered in 1896, have been known to have medical effects. In humans, tissue becomes red and inflamed and eventually cancerous if you expose it to X-rays for too long. This is why the X-ray technician goes into a lead-plated room when you're at the doctor's. We'll see a lead-plated room in one of the laboratories that we'll investigate just a little later. Now, a quick note here, gamma rays, which you see here, are even higher energy than X-rays, but they produce much the same biological effects, just faster and meaner. You want to avoid high gamma ray dose exposures. There's a second type of radiation that's important for our story, and that is radioactivity, and we see that with the purple background here. Radioactivity is reasonably straightforward. Atoms would like to be stable. They want their nucleus here to have the same number of positively charged protons and neutral neutrons. If they don't have this, they start shooting out particles and energy until they can get balanced. So here we have a heavy nucleus, and there's three main types of radioactivity: gamma rays, beta particles, which are simply electrons shot out of an atom, and alpha particles, which you can see have two protons and two neutrons. They're essentially the nucleus of a hydrogen atom. Plutonium-239, which was the product made by the reactors at Hanford, emits alpha particles, these helium nuclei up here. Uranium-235 also emits alpha particles. An important radioisotope that emits beta particles is carbon-14, and so on. Across the heavier parts of the periodic table, we can find radioactive elements that emit these different rays and particles. So radioactivity is the decay of a single atom. Finally, down here, by the bar that I can't get rid of, but there we are. Finally, down here, we have fission, and we've got enough of this picture. Fission occurs when a free neutron collides into a heavy nucleus, collides into this setup right up here, and then breaks that nucleus apart, resulting in fission fragments, which are simply lighter elements, as well as more free neutrons. These free neutrons then go on to break up more heavy nuclei, and so fission occurs in a chain reaction. This is the process that the reactors, or they called them piles back in the 40s, that the piles at Hanford used to produce plutonium. This is also the mechanism that works inside the atomic bomb, or inside both styles of atomic bomb using uranium and plutonium, but that happens much more quickly than inside the reactor cores at Hanford. So we have rays up here on the electromagnetic spectrum. We have radiation, and we have fission. These three important types of radiation that are foundational for our story. Now, a quick romp through geography, and I promise the prologue is over. Maybe a lot of us are familiar with wartime Manhattan Project geography. There are the three big installations that are in the popular mind. They are Oak Ridge, where uranium-235 was produced. This is the uranium that went into Little Boy, the bomb that devastated Hiroshima. There's Hanford, which we're focusing on today, where plutonium was produced. This was the fuel that fueled the device for the Trinity test in July 1945 in Alamogordo, New Mexico, and it fueled the bomb that destroyed Nagasaki on the 9th of August, 1945, 3 days after Hiroshima was bombed. Down here, you can see Los Alamos Laboratory. This, of course, is the most famous of the labs. It's the physicists who were the hotshots in the Manhattan Project. And of course, there's a movie coming out later this year about Robert Oppenheimer, who was the head physicist at Los Alamos and the head of the bomb project, the scientific head of the bomb project, I should say. Los Alamos is the place that gets movies made about it and TV shows made about it. We're going to visit Manhattan Project installations that are not on this map. One of the great things about maps is they tell you as much with what they don't show you as they tell you with what they show you. So we're going to visit a part of the Manhattan Project that was so obscure that laboratories don't tend to show up, that their labs don't tend to show up in our atomic histories. So let's finally get to our history story. I'd like to introduce you to the folks who began the medical section of the Manhattan Project. Now, if we could see each other, if we were all in the same room, I would ask you to raise your hand if you'd ever heard of the medical section of the Manhattan Project. But I can say from experience that when I've done this, I don't get a lot of hands going up. The doctors and the biologists who worked for the Manhattan Project did so in the shadows. They were in the background behind the physicists who designed and built the bomb. Why have a medical section? The reason that Leslie Groves, the general who directed the entire Manhattan Project, started the medical section in 1943 is a little unclear because the medical section had so many jobs. Groves chose this man here, Stafford Warren, who's the tallest person in the photo, standing on the edge, to lead the medical section. Warren left his professorship in radiology at the University of Rochester's medical school to be commissioned as a colonel in the Army Corps of Engineers in the Manhattan Project. But Groves picked him because he was deeply familiar with X-ray research. And in fact, he helped develop the technique for mammography in the 1920s when he was a professor at the University of Rochester. He also helped design and build the new medical school building at University of Rochester. So he had some scientific chops and some bureaucratic chops. He led this organization that had, like I said, a lot of missions. When Warren took up his commission in 1943, the first thing that he did was travel to Oak Ridge, where he organized the construction and the staffing of the hospital for that new secret city. The hospital was designed to care for the workers who were producing enriched uranium and to care for them in case of a radiological accident on the production floor. Now, providing hospital care sounds like a noble mission, and it is, but Warren operated with a blurry boundary between therapy and research. I need to jump here out of chronological order a little bit so that we can get to March of 1945, when on Warren's orders, Dr. Joe Howland injected Ebb Cade, an African-American man who worked at Oak Ridge on the uranium production floor. Cade came to the hospital after a car accident, and without his knowing, Howland injected him with liquid uranium. This isn't a new story. I really recommend Eileen Welsom's excellent book, The Plutonium Chronicles, if you'd like to know more about the human radiation experiments that the medical section took part in. But I'd like to give you a sense that under Warren, the section had an ambiguous mission to offer care, but to also produce radiological data, in this case, at any cost, without the consent of a person who had no reason to even expect any kind of radiological exposure in any way. Let's jump back to 1943 now. We'll meet our second key historical figure after Stafford. So here's Stafford Warren. Over here in the background is Dr. Loren Donaldson. He worked as a professor of fisheries at the University of Washington and had served on the joint Canadian-U.S. Pacific Salmon Fisheries Commission before the war. Warren asked Donaldson in mid-43 to start a new laboratory at the University of Washington, innocuously called the Applied Fisheries Laboratory. What do you do with the Applied Fisheries Laboratory? Well, we'll get there. At the lab, Donaldson and his initial team of 4 biologists exposed salmon and steelhead trout to X-rays. This lab is going to be the first stop on our journey to see how salmon became data production machines and why the UW lab mattered for Hanford. So Stafford Warren and Loren Donaldson. We'll meet this gentleman here later, but we'll get there. Here is the Applied Fisheries Lab at the University of Washington in 1943. It was right on the shore of Lake Washington, roughly where the School of Aquatic and Fisheries Science still stands today. This building was built during World War II and stood through the 1970s. The photo that we just saw of the 4 medical section folks, that was taken at the front of the building over here on the porch. And the salmon that we saw in the straitjacket was on the edge of one of these ponds out on the lawn. It was here in October 1943 that Donaldson and his team of biologists first used X-rays to irradiate adult salmon so that they could then spawn those salmon and study how their offspring developed after having been exposed to X-rays. Again, let's remind ourselves why they were doing this. The thread about salmon producing data in the lab, which scientists could then use in the environment, is at the foundation of the Applied Fisheries Lab story. Warren wanted Donaldson to produce data for 2 reasons. And I should point out that Donaldson in 1943 didn't realize that he and his lab were working for the Manhattan Project. Secrecy was so important that they didn't find out until probably the middle of 1943, as we got closer to the Hanford reactors coming online. Let's remind ourselves why Warren wanted salmon data. There's 2 reasons. The first reason is precisely because Warren knew that the plutonium production reactors at Hanford would come online in 1944 and 45. And he knew that they would use water from the Columbia River to cool their immensely hot cores. This water would then go back into the river, full of radioactive fission fragments. Think back a couple slides. Remember that neutron smacks into the nucleus and fission fragments fly out. Those poured into the Columbia River and were exceedingly hot. They were actually very hot temperature-wise too from the core, but they were hot radioactively. Manhattan Project officials worried that the hot effluent from the piles would produce hot fish, that the Columbia's valuable salmon fishery would be impacted by radiation, and that this would just not only hurt a $1 billion a year industry, but it would be really bad for secrecy at Hanford if salmon and steelheads began dying by the thousands, by the millions in the river. Since the reactors were not even built in 1943, Donaldson's lab used X-rays to irradiate the fish because that was the best thing they had. I really want you to hold on to this key part of the story, that the UW lab is the Center for X-ray Research. So there's a second reason that Stafford Warren, the head of the medical section, wanted this data. And that reason has to do with knowing about human responses to the biological effect, or the biological effects of radiation in human beings. Warren believed that he could use data from hot fish to learn about what radiation from the atomic bombs, that again, were not constructed yet, but were in the pipeline, what they would do to human beings. Warren even brought his medical doctors from the medical section to visit the UW lab. Joe Howland, who injected Eb Cade with plutonium, visited the University of Washington lab to learn about the biological effects of radiation to different tissues and organs. Now, Warren's assumption about X-ray fish data producing human bomb data is a bit of a leap, because as we saw on the radiation slide, X-rays and the products of fission are not exactly the same. But in these very early days of the atomic age, X-rays were what the medical section could use, and they're what so many people in the medical section had experience with, so many of the medical doctors who had worked as radiologists. Now, you might be thinking that there's another leap here, which is a leap from the health of fish to the health of human beings. And you'd be right about this. In 1944, Warren wrote a letter to Lauren Donaldson about blood production in fish. Since fish are not mammals and they don't have bone marrow, which is where we produce our blood, Warren wanted to know what the story about blood was. Now, it turns out, Donaldson responded to him, that salmon produce blood in their kidneys. Warren wanted to know about blood production and then about kidneys in salmon, because blood production is one of the things worst affected by exposure to radiation. If you think about it, cell division is happening all the time, every moment as blood is produced. And so because cell production is happening continuously and rapidly, even a short exposure to radiation affects hemopoiesis, blood production. So Warren wondered about this, but when Donaldson answered his question, Warren simply directed Donaldson and his biologists to look at the health of kidneys. And we'll see some kidney tissue in just a moment. But before we do that, let's recap. The fish exposed to X-rays in the Applied Fisheries Lab at UW were meant to make data about fish exposed to reactor effluent in the Columbia River once Hanford's reactors got up and running. They were also meant to produce data about living human beings in Germany, probably in 1943, because the war was still raging. Maybe Japan. But the fish were meant to produce data about human beings exposed to radiation from a fission bomb. I've talked a lot about X-rays, so let's take a look at an X-ray tube. Here you see this massive X-ray tube that the Seattle biologist used to expose fish, to irradiate fish. Here is where the first fish became hot in October 43. I'd like to just mention a couple notes on the technology, because I find this stuff really fascinating. Warren secured this X-ray apparatus from Strong Memorial Hospital in Rochester, New York, which is the teaching hospital at the University of Rochester, where he had been on the medical faculty. He had his right-hand man, Francis Bishop, who I just quickly pointed out without naming in the slide a couple slides ago. Francis Bishop brought this used machine across country and then set it up, and he calibrated it with the fisheries biologists, because they really didn't know anything about X-rays. So we have this pre-war technology here. In the example of the brand it's got a great name. It's a picker weight shockproof therapy unit. So there's the X-ray tube, and the tube itself is just right down here and sends X-rays out as a beam like this. Now, you can also see a wooden cart. The wooden cart does not look fancy. The wooden cart is what the biologists filled with water, and then they ran a hose so that the water would run and oxygen would move through the cart. They put salmon, the salmon that they were going to irradiate, into a sling that hung off the side of the cart, and the salmon would sit basically happy inside the cart full of water while the beam of X-rays irradiated it. To make sure that the exposure was uniform, the scientists took the fish halfway through the exposure and flipped it so that each side of the fish got the same amount of X-rays or of X-ray exposure. What I love about this cart is that it's pretty low tech. A big element of the atomic story that so many of us get taught, and the story that's told at Hanford, is that from the earliest days, there were modern and amazing technological achievements being accomplished. Just getting the piles to work was this amazing feat of science. They were on the frontier making breakthroughs. But in the UW lab, we see this pre-war X-ray machine and a wooden cart. This is not the shiny atomic future that makes it into the movies, but this is the way that real Manhattan Project science took place. Most importantly, I'd say from this picture, we should take away that we see a really controlled laboratory space. We're inside that leaded walled room. We're inside this room so that the fish will be exposed to X-rays, but the biologists won't be. So we should ask ourselves a question right now, which is, what does this lab, this controlled, this really focused space, what does this have to do with the Columbia River, which is anything but uniform in its topography, its hydrology, its bathymetry? If you walked or swam in the Columbia, you know that it is not a docile place. And I would suspect it's not very much the same as this wooden cart with a tank where they irradiated a restrained fish. Okay, let's file that question away. And we'll finish this slide with a quick reflection on measuring radiation in 1943. The medical section doctors used Roentgens as the unit by which they measured radiation. Roentgens were named after Wilhelm Röntgen, who was the discoverer of X-rays way back in 1896. Officially, the Röntgen was a measurement of electric charge in a volume of air. Again, not a physicist, don't get too worried about that. What we need to know is that it simply was the unit. And this was true for people doing biological research in radiation across the globe. When the Seattle biologists put a fish in this box, they simply set the X-ray machine to a certain time in order to expose a fish up to, say, 100 Roentgens or 100 R, or 500 Roentgens, or 1,000 Roentgens, or 5,000 Roentgens. A quick note, for those of you who are familiar with biological radiation units developed at Hanford in the Cold War, we are just way before a time, way before absorption doses like RADs and REMs. They didn't think in those terms at all in the 40s, or certainly not in the medical section. So in 43, 44, and 45, Donaldson and his team really didn't even know how to use Geiger meters or scintillation tubes. So what they did was simply calibrate the X-ray machine. They'd been taught by the expert, Francis Bishop. Then they let it rip for a certain amount of time. That resulted in, like I said, fish that were exposed to certain levels of radiation. Once those fish were irradiated, they went into the troughs that you see here. This is the main room at the Applied Fisheries Laboratory. Again, not cutting edge looking technology. You know, these are troughs that had been hanging around the School of Fisheries since World War I. What we need to take away is that this trough here might hold a population of a couple thousand little salmon, so fingerlings and fry, that were exposed to 100 Roentgens. This trough might hold salmon that were exposed to 250 Roentgens, and this trough back here would hold salmon, a population of salmon exposed to 500 Roentgens. When Donaldson and the biologists got their work off the ground in 44, they were only exposing salmon to very low levels. So 50 Roentgens, 100 Roentgens, 250 Roentgens. But Warren wanted data about what an atomic bomb would do. He wanted high exposure data. So he visits the lab late in the winter of 1944, and he tells Donaldson he's got to just ramp it up, that he has got to up the ante and start exposing salmon to much higher levels of X-ray irradiation. Donaldson did. I think, just as an aside, I think that might also be the moment when Donaldson learns that he's part of the Manhattan Project. Warren and Donaldson went fishing for an afternoon, and I suspect that's when they had the talk. By the way, your contract is with the Office for Scientific Research and Development, but your payment is actually coming from the Army Corps of Engineers. Donaldson did amp it up. And so by 1945, by summer of 1945, the Seattle biologists had a sense of where things stood in terms of the biological effects of radiation. They did see high mortalities and high deformity rates in fry and fingerlings, so think baby fish, spawned from parents that were irradiated over the 1,000 Roentgen threshold. They also saw very high exposures like 10,000 Roentgens were simply lethal to adult fish and to fry and fingerlings, and actually really to eggs. Eggs never developed when they were irradiated at that level. But below 500 R, Donaldson and the biologists only saw negligible deformities and mortalities. They also saw significantly less in the somatic insults in the way of somatic insults at these levels. You see, I have these three inset pictures here. These show kidney tissue from young fingerling salmon. And they're lined up in order of increasing exposure. So this is a test sample here. And you can see nicely defined cells. You can see, this is a good looking picture. Again, I don't have a BA in biology, but this is a good looking picture. You can even see the structure and the nucleus inside of some of the cells. This picture here in the center is a salmon whose parent was exposed to 250 R. So, or still a low dose, but enough. You can start to see differences in the cell form, and you can see that this is a much darker picture, that the radiation insults on the cellular level begin to be visible. Over to the right here, you see a picture of a salmon fingerling whose parents were exposed to 500 Roentgens. And you can start to see the cells beginning to fall apart. Stuff gets way more irregular and way darker. There's more dead blood cells. That's in part what cell death in part is what causes the darkness in the pictures. It's a quick visual snapshot, but I'd like you to just compare option 1, which is no exposure, with option 3, which is 500 Roentgens. Interestingly, 500 Roentgens sort of becomes the boundary, though. After 500 Roentgens, the somatic data that you can see here, this microscopic data, goes really off the rails. But below 500 R, the fish are basically living, and things don't seem so awful. So by 1945, you have the biologists working with this sense that 500 Roentgens is a real threshold, and that anything below that, in the grand scheme of things, is tolerable and actually even safe. Safety. Hanford loves to talk about safety. This is a word that people who have a historical interest in Hanford, it was as safe as reasonably possible. Not Alara, but safety built into the DNA of Hanford. Let's turn our story to the site now. This is a great map of Hanford in the early days. You see the 3 wartime reactors, the 100, the B reactor, the D reactor, the F reactor. 100 simply means reactor area. The 200 areas, where the canyons were, where they separated the uranium from the plutonium through a series of chemical baths. You see the 300 area where science took place, and then the towns of Richland and Pasco and poor sweet Kennewick, always left on. I mean, either Pasco or Kennewick gets it in Hanford stories, but I'll point you back to this fission picture over here, because of course it's fission that makes the 3 piles at Hanford work. It's fission that produces plutonium out of uranium. So here's our quick map introduction to Hanford. I'd like us to zero in on the 100F area. So here we have a great aerial view of the whole area, and it's along the curve on the Columbia. You see White Bluffs across the way. Our story at the 100F area begins here at the water intake, where 35,000 gallons of water per minute were pulled out of the Columbia River by the pumps in the massive pump house in order to go through an underground sewer line to cool the pile's reactor core over here. 35,000 gallons of water per minute. That's significant, especially when the Columbia is flowing really low at the end of the summer and in the fall when we're furthest away from snowmelt. All of a sudden, all the reactors pulling water out of the Columbia to cool, or all the pumps pulling water out of the Columbia to cool the reactors, that gets significant. But for right now, we have water going through the F reactor, and it cools that reactor down so it doesn't melt down. We see these ramps that take spent fuel, the fuel that will be taken to the 200 areas by rail. And we see the rail line here. But off in the corner, there's this little blip. And in the blow up, you might be able to tell that it's a Quonset hut. This is the Hanford Fish Lab, built in the winter of 1944. At the Hanford Fish Lab, no, that's a lie. 1945, built in the winter of 1945. Sorry, I'm all out of whack. Built in 1945, and it really was just a Quonset hut. There's a sewer connecting the reactor to the Quonset hut so that they could pipe effluent directly from F reactor into the new fish lab at Hanford. Dick Foster, whom we've not met nor seen a picture of, but we will in a moment. Dick Foster was one of Lauren Donaldson's graduate students at the UW lab. He was one of those first original 4 biologists. He became the director of the Hanford Fish Lab in 45. He goes over there to test fish in the real deal, effluent from fission, no longer just X-rays. Here's an overhead view of the fish lab, and this view is actually from 1952, but you can see the original building here. Here's the Quonset hut. There are ponds, just like there were at the lab in Seattle. The fish lab at Hanford really is just a mock-up of the Seattle lab. The thing that I'd like to point out in this slide is right here coming into the roof. This is the pump where the reactor effluent came in and was pumped down into the lab. What's really fascinating about the fish lab's origins are that when Stafford Warren asked Donaldson to found it, Warren got together a bunch of medical doctors, because those medical doctors, again, wanted knowledge about what was going to happen. At this point, they knew it was going to be Japan, what was going to happen in Japan when the atom bomb was used. So they got together, these doctors and fisheries biologists, at UC Berkeley in June of 1945, and they were the ones who put together the research program for Hanford's lab. What did this research program entail? Here's Dick Foster standing at the troughs in the Quonset hut at Hanford, looking terribly scientific. He's displaying fingerlings to us, I think. You see, I hope, the familiarity of the troughs. The thing about the Hanford troughs is that they differed a little bit from the UW troughs. Remember, back at UW, this trough would be filled with 100R fish and this trough with 250R fish. At Hanford, this trough was filled with pure river water. This trough was filled with 10% effluent from the reactor and 90% river water. This back in the middle here was 50% effluent and 50% river water. And then at the far back was pure effluent, 100% radioactive hot water that came out of the reactor core. The plumbing was immensely complex, and you can kind of see that. It took them about 6 years or 6 months to get the plumbing right. So they only actually started getting good data from the Hanford Fish Lab by October of 1945, after the bombs fell on Hiroshima and Nagasaki. But the data that they got from having fish continually living, they put, again, small fry and fingerlings in these troughs, fish continually living in effluent, they started to get data that showed them essentially what the UW showed them, but in a different way. What it showed them that there was a threshold, and that fish that were only exposed to a small percentage of effluent were on the whole statistically okay. There were small rates of deformity. There were low mortality counts. Whereas fish exposed to high levels of effluent were not okay. The fish that lived in the 100% effluent had high mortality rates and significant deformities. This general trend backed up the UW data, backed up the X-ray data. And it became incredibly meaningful at Hanford for 2 reasons. Reason number one, and I hope you're starting to see this, this was kind of our first thread, is that these medical section biologists trust the lab. They are used to doing laboratory research. Now, they're familiar with field research, but they believe in the data that comes out of their laboratories. The second reason that data from the fish lab at Hanford became significant was simply the scale of Hanford. If you've driven from Richland to Mattawa, you know that it takes a long time. And that's on a good highway today. Foster only had at any given point 1 or 2 assistants working for him in the lab, and they were often busy doing research and maintaining these thousands of fish that they had in the troughs and out in the ponds. They did not have time to drive over 170 miles per day to make collections on the river all the way from Priest Rapids down to Richland on dirt roads. It was simply impossible to collect water and to try and fish for fish, given the scale of Hanford. Now, because the data from the fish lab showed that low effluent exposures were essentially safe, Foster was able to argue, look, all of the water, all of the effluent that has gone through the reactors and then sits in a holding basin for a while and then goes back into the river, this 35,000 gallons per minute, by the time it goes back into the river, it's not that hot. And the huge pipes out in the center of the river that pour the effluent back into the Columbia, it's only around them that you get anything like 100% effluent. Most of the Columbia River is like this trough right here at somewhere less than 10% effluent. And if the fish are safe in the trough, mustn't they be safe in the river? We see this thread of lab data producing environmental data, and it's powerful at Hanford. The story's got one more part, and I see that I've got like 10 minutes, so we're just going to move, and it's going to happen. It'll be okay, because it'll be nice to have questions and answers. But this is a really important part of the story, because Hanford tends to be talked about as an island, a radiological, a uniquely radiological place, the most polluted place in North America. But the medical section story shows already that it's tied to this lab at the UW. And now we're going to see that Hanford is tied to the occupied Pacific, to the trust territory of the Pacific Islands. And I'll apologize for the blurriness of the map, but this is a really handy map. We're going to follow Foster and Donaldson and Warren now to the Marshall Islands, and in particular to Bikini Atoll in 1946 and 1947, because all of these men were involved in the atomic tests during Operation Crossroads at Bikini, and in the science that followed up after those tests. Here you can see shot Baker at Bikini Atoll in 1946. Warren and Donaldson went to Bikini in 46 in order to do radiological safety, but also to collect fish in order to study them, because they were interested in the biological effects of radiation from an atomic bomb, and because they already had lots of fish data. The biologists, and I can't emphasize this enough, see continuity from X-rays to reactor effluent to free neutrons and fission products from the bombs, because they're so used to thinking about the biological effects of radiation as they were lumpers, not splitters, if you use that terminology. They were thinking in terms of a rational research system, a research program that they had been working on since 1943. And going to Bikini just allowed them to expand the scope of their research. So Warren and Donaldson go to Bikini in 46, and they witness the Bravo shot, and they go into the lagoon the next day to collect fish. If we think about Bikini Atoll, so here's a group of the UW scientists. This is Donaldson. You can see Donaldson's back right here, if you've looked at enough pictures of Warren Donaldson. The biologists thought of the bomb as their X-ray tube, and they thought of the lagoon at Bikini as their new trough. And they were going to go out and collect fish that could start to show them what fission did in nature. They returned in 1946 because they and the Navy and the newly created Atomic Energy Commission wanted to know what radiation did over time in nature. They learned to use Geiger counters or Geiger meters and these devices called counters in Bikini from chemists who came from Los Alamos laboratory. So what they started doing with their samples at Bikini was they would still take a sample from a fish and get organ tissue. But what they started to do was they'd put it on a little plate like this, made out of porcelain or out of metal, and they'd put these plates into muffle furnaces, these little ovens that could heat the samples up to many 100 degrees Celsius. These turned the samples eventually into ash. Here's Dick Foster, not wearing a shirt. It was the tropics. They never wore shirts. It was also a gendered space. They were only men in 46 and 47. Women don't become a part of the story scientifically until the late 50s. But here's Dick Foster, having come from Hanford, looking at an ashed organ of a fish from Bikini Atoll, which they would take this ashed sample on the plate and put it inside a radiation counter and let a Geiger meter actually count the number of radioactive decays that occurred. So this is a little different than when they were looking at those pictures. Remember, you saw the kidney tissue. This is a different way of collecting data. But they took the data from the electronic radiation meters and the counters, and they then proceeded to treat it just like they treated those visualizations and that population data that they got at the UW lab and the Hanford lab. The research program kind of won. So even though their techniques changed, and even though where they studied changed, the way they thought about radiation didn't. I should also point out that even though they're collecting field samples, they always trust the lab to make data. Here they are preparing samples in the field. They would take these ashen samples and send them back by military mail to the lab in Seattle to be counted, because they didn't believe that they could get good data out in this kind of crummy field laboratory on these plywood benches. They really believed in the power of the lab to make data. Okay, so I'll try and conclude now by bringing us back to Hanford. Safety. I hope in the midst of this whole story that I've been able to show you that the medical section biologists who worked at the UW and who worked at Hanford believed that they could take data from a lab, fish data from a lab, and use it to indicate that there was a threshold of safety in nature. They certainly saw this in Bikini, because when they saw populations spring up in 1947, when they saw fish populations rebound after 2 atomic tests, they thought, oh my goodness, these atomic tests had almost no bearing on the actual health of the entire environment here, of the entire, of the biotic populations on the landscape. I want you to look at this picture here, which is from the 1970s, but it's from a talk that Dick Foster gave. He was talking to Washington state officials when he gave this talk, and it's a sort of imagination of Hanford. Here's one of the reactors of Hanford functioning as a healthy environment, because you can see the reactor effluent going into the river. But then you can see the water intake for the city of Richland. You can see farmers, I guess now growing grapes on the north side of the river. You can see people fishing. This man's hunting, and he'll get his goose out of the river. There are people water skiing, and the ducks look just so happy in the river. Dick Foster so believed in the threshold of safety that was proven to him by his lab work that he could imagine Hanford in this way, a totally natural environment where radiation is not just normal, but it's safe. This is one of my favorite pictures of Hanford ever. Just let it sink in. A totally normal space. I'll leave you with a quick story about how that at the beginning of the talk, I said that I think that these fisheries biologists, I think the medical section, had a role in constructing the DNA at Hanford, the scientific DNA at Hanford. And here's an example of what I mean by that. In 1949, the US Public Health Service tried to do a survey of the Columbia River that would look at river health in general. So not just the radiation, but the biotic health. They'd look at the impact of the Grand Coulee Dam. It was the Public Health Service had big plans. Herb Parker, who was, of course, in charge, the health physicist in charge of the Health Instruments Division, you see their logo here that Herb was really proud of. He designed it. Herb was also Dick Foster's boss in 1950. Herb caught wind of the US Public Health Service's plan to intrude on Hanford from his perspective. And so Herb set Dick Foster and his laboratory data onto the Public Health Service. And at a meeting, the April 1950 meeting of the Columbia River Advisory Board, which maybe folks have heard of, they called it CRAG. Maybe you've heard of that. CRAG evolved over the years and eventually started to hold the Atomic Energy Commission to account. But in the 40s and early 50s, CRAG was really just a booster club for General Electric and the Hanford mission for plutonium production. At this meeting, Foster relayed all this data to Washington State and Oregon State officials and to AEC officials, Atomic Energy Commission officials from Washington, D.C., to prove why they had a handle on things radiologically, why the river was safe, why the salmon fishery was safe, and why the United States Public Health Service certainly did not need to come in and do a survey of the Columbia. It worked. The Public Health Service would send a team of scientists out, but they kind of got stuck in temporary buildings down in Kennewick, close to where the Reach is now. Eventually, they sort of ended up in the 300 area, but they really spent most of their time rifling through Dick Foster's data. They never got into the river in a meaningful way. So I'll leave you with this thought. We know, or folks who are interested in Hanford cleanup know that there's oftentimes scientific rationales for why something is safe or for why a type of remediation couldn't happen. And I hope that I've convinced you in some small way that the first biologists who worked at UW, at Hanford, who were intimately knowledgeable about Bikini and Enewetak Atoll, the Applied Fisheries Lab spent a decade and a half going to field seasons in the Marshall Islands. I hope that I've convinced you that they helped create this sense that lab data shows us a threshold for safety, and that argument has been repackaged and reconfigured and resold for decades at Hanford and continues to be sold today. So thank you for your time. You saw a fish in a straitjacket, so it can't have been that bad. I'm grateful to share the story of Hanford's origins with all of you.
Thank you so much, Josh, for fantastic, incredible storytelling and explanations of this history. And we're now going to open it up to questions. So please feel free to put your questions either in the chat or in the Q&A at the bottom. And we do have a few. So the first question is, out of curiosity, did these researchers end up dying of natural causes, or did they start to experience radiation symptoms because they were exposed so much over the years?
Oh, so this is fascinating. This question actually comes up a lot. And so the short answer is no. Almost all of these people live to a ripe old age. I should say that Lauren Donaldson, you saw the picture of the guys wading out into Bikini Atoll right after Test Baker. Lauren Donaldson got the atomic bomb disease after Test Baker in his notebook. And I should say that his papers are all at the University of Washington because he spent his whole career there. So you can go to special collections and just call up a box and literally look through the notebooks that these guys took to Bikini, that these guys fill page after page with salmon data from Hanford and from UW. But Donaldson got sick. He was vomiting. He was lethargic. None of his hair fell out, but he got the radiation sickness from going into Bikini Lagoon, and I suspect other biologists did. But no, a lot of them lived into their 70s. Warren lived, I want to say he was born in 1896 and he died in the 1980s. Donaldson died in the 90s or late 90s, I believe. A lot of them retired to Bend, just outside of Bend, before Bend was a thing. So in the 80s, you can actually read especially, I came across a lot of letters to the editor in the newspaper in Bend, especially when there was the plant decommissioning, like when there was the whole Washington Public Power Service debacle in the 80s. And then when Trojan power plant was decommissioned just outside of Portland, you see letters from the editors from some of these guys who worked for the Manhattan Project saying, oh, these people don't know anything about radiation safety or how atomic energy works. And if we were in charge, energy would be too cheap to meter. So no, a lot of them rich, full lives.
Okay. Thank you. This is a longer one. If you want to read it, it's in the Q&A.
Yeah, I'm looking at it.
Okay. Thank you for the important and fascinating presentation. Numerous times you referred to trust and trusting the data. During your research, did you come across any examples of government or contractor efforts to educate the public and to shape public opinion and political support for the nuclear enterprise, particularly in light of the prevalent public opposition to nuclear weapons and their horrific effects when used? And I'll wait on the other two questions.
Yeah, for sure. Yeah, you can both Warren and Donaldson were immensely able public speakers and good at working a crowd. And Donaldson had, as far as I can tell, a direct line to the Seattle Times. So the Applied Fisheries Laboratory shows up in the Seattle Times. If you go back and look at, especially after they go to the first couple atomic tests in the Marshalls, Donaldson will be there. You know, there'll be a picture of Donaldson on the beach at Bikini in like the local section of the Seattle Times. Warren really evangelized for needing to do atomic research. And you could skeptically look at that and say he was always trying to drum up funding for this network of scientists that he oversaw, even after the medical section disappears because the Manhattan Project disappears. These laboratories persist through the 1980s. And at UW through the 1980s, the 1970s at Hanford, it gets molded, it gets kind of folded into what becomes Battelle. But Warren goes around, and Warren was of the mind that he advocated for the argument that dropping the atomic bombs saved lives because more people's lives were spared if the Americans had to invade Japan, that more lives would have been lost. So Warren really vocally advocates for that position until his death. I don't think he ever changes his mind about that one. And Foster, you can actually, if I'm industrious, maybe I'll find the link and copy it into the webinar chat. You can actually go on YouTube and find GE, General Electric, when they were the prime contractor in the 50s and 60s. They ran a TV show where they'd bring Hanford workers out. And Dick Foster, actually, you can still see on YouTube a show where Dick Foster shows people fish and shows folks how they monitor the Columbia and what the radiological situation is. So they really, they trusted their own data. And I'm going down in your question. You make this remark, can you comment on the question that Kate Brown's book, Plutopia, which is awesome book, raises? How could so many brilliant scientists and engineers seemingly not recognize the profound environmental problems which the nuclear enterprise creates? And I'll say that after 10 years of graduate study, I wish I had a better answer for you. But I think a lot of it has to do with how scientists were held an extremely powerful social position in the mid-20th century. This is before the environmental movement of the 1960s. This is before scientific data starts to be questioned in the general public in a meaningful way, I would say. Rachel Carson only publishes, these folks are contemporary with Rachel Carson. So Silent Spring hasn't made a splash yet at this point. And I think they really believed in good data, meaning I think they just believed in their data. And they all wanted to beat the Nazis and then the Japanese, and then they all wanted to beat the communists. I think another part of this answer is that I don't think these guys ever got out of wartime mode. The first thing that Stafford Warren did when his crew, when the biologists from Seattle, when they all got to Bikini in 1946 for the first peacetime atomic tests, was he showed them the stolen Japanese footage that the Army got from the Japan Film Board of Hiroshima and Nagasaki. And what I think he was trying to do when he did that was to say, look, guys, the war is officially over, but we've got a wartime stance always. When you look out and see these pristine tropical beaches, you should be seeing the hospital in Hiroshima. You should be seeing the streets of Nagasaki, because we're always in wartime. So that's not a super clear answer, but I think they've got this wartime kind of stance and this high view of their own social position, and that makes them believers.
Thank you. When it came to extracting data for human safety considerations, did the salmon offer something different than other types of animals in the Manhattan Cold War Project testing network?
Awesome. Thanks, David. And nice to see you. I have the pleasure of being acquainted with Dr. Bolingbrook, who has done amazing research on Hanford and especially on the elk at Hanford. So big shout out. the salmon, one of the points is that the salmon they do two types of work. They do the work about the Columbia River fisheries, and they do the work about human beings. There is animal testing on mammals at the University of Rochester, but that research doesn't really go anywhere. It goes on during the war, but it doesn't continue in a meaningful way after the war. It's just sort of a weird contingency of history. People maybe who know the atomic story more broadly may know and may recall pictures of goats and other mammals on the decks of the ships at Bikini Atoll for Crossroads, because they wanted to see what atomic blasts would do to those animals. That was the Office of Naval Research that coordinated that effort. So that actually was never part of the Manhattan Project or the medical section. And the two groups they talked with each other, but not that much. They certainly didn't change each other's research because of that. I'd also point out, just for Hanford, Dick Foster and Leo Bustad, who helped run the the research farm up at 100F, whose official name I'm blanking on because it's been a long day. They talked to each other, certainly. And so the fish folks and the terrestrial animal folk end up in the same lab at the 300 area in Hanford eventually. But at the get-go, it's really this bizarre fish story. It seems supernatural to me because it seems super-natural to me, very natural, that fish just were what they used, because I've researched it for such a long time. But yeah, if you zoom back, it's a totally weird choice to choose a non-mammal to get this data from. I've just say, as research animals, the other key part of this is Donaldson gets picked in part because he's tied into the state fisheries or the state hatcheries network, and they can get uniform salmon to use. So they're good experimental animals, but that's kind of where that lies.
Okay. I think the health outcomes of those who waded into the lagoons would show more problems like Donaldson's or lymphatic cancer or disease. Is that true?
So yeah, again, the health of the health of these folks. Like I said, I've not experienced the only death I know of from the Applied Fisheries Laboratory was created because someone ran an errand for the Atomic Energy Commission. And to go and give a talk, and their airplane crashed. That's literally the only the only premature death that I know of.
Was this research the only source for the claim of a 500R threshold?
Oh boy, yes and no. So I would say at Hanford, the answer is kind of yes. And I say that just because Hanford did, Herb Parker and Dick Foster and some others at Hanford did such a good job of putting boundaries up around the site and only operating with the assumptions that they had from their data, so that yeah. And they published in the gray literature. So I mean, they published reports that circulated through the Atomic Energy Commission. So other biologists saw this. Oak Ridge had a powerful biology department. But I should say that one of the hitches here, and actually it's a corollary to the story, is you never maybe heard me use the word ecosystem, because these folks from the medical section were not ecosystem ecologists. And actually, they hated ecosystems ecologists. Things got a little petty, and especially once in the Atomic Energy Commission, it's the Division for Biology and Medicine that doles out funding to people doing biological research across the country. So when these folks are competing with funding to get out to Bikini to do work at Hanford, they really take a dim view of ecosystems talk. And if you go through you can look through just the reports of the Hanford Aquatic Biology Department, and then by the late 60s, just the biology department. And you'll see that there's very little ecosystem talk until the mid to late 60s, the late 60s. And in some ways, that's because new graduate students are coming to Hanford and they were trained in ecosystems ecology. But in other ways, that's just because ecosystems were hot. And so you could get funding if you called your project an ecosystems project. But these folks, they believed in this tradition, and they believed in it to the exclusion of other traditions that might say, hey, why would you pick 500 Roentgens? Hey, why wouldn't you update your view? I'll just another quick yarn. When a lot of these guys get involved in 1954, the Castle Bravo disaster, where the physicists at Los Alamos designed a thermonuclear device that turned out to have a much higher yield than they anticipated. It created fallout at Bikini. The fallout from the blast at Bikini traveled 100 miles downwind and fell like snow. People say this in the record on Rongelap Atoll. And some folks from the Applied Fisheries Lab became caught up in this story because they were the experts by the mid 1950s on irradiated environments. And so they did a lot of research into whether foodstuffs would be safe. The folks at Rongelap had to be evacuated for 3 years, and they were sent home. And it's this network of scientists who went and looked at, can you eat the fish? Can you eat the food that lives in Rongelap? And this is going to get real esoteric, but over and over again, the biologists talk about a tolerance dose. So the idea, and I kept using the word tolerance because in the first decades of the 20th century, there was an idea that animals can tolerate a certain amount of radiation, that there is this safety zone. And once you get above that, you're in danger, but you can tolerate so much. Because of genetic research and because of more data coming in about radiation, by the 1950s, the US Public Health Service got rid of the tolerance dose and implemented the maximum permissible dose, which is a subtle change. But to go from you can tolerate a certain dose to, well, we need people to work in places where there's radiation, so you're only allowed to have so much. Those are two totally different things, because the permissible dose gets rid of this notion of safe exposure. But this crowd would look at the tables that the Public Health Service published about exposure to certain radioactive elements, and then not to pen up. Then they would misquote the tables to say that the Public Health Service tolerance doses tell us this, when the Public Health Service had abandoned tolerance doses. So that's just a quick vignette to show that these folks locked into their way of seeing and didn't change over decades.
Thank you for that. And just to clarify, you're talking 500 R or 500 milli-R?
Oh, 500 R, not milli-R. Yeah. Milli-R, well, that's a different story. That's too much. 500 R, yeah.
Okay, thank you. I don't know if you're familiar with this book, but how did these guys deal with David Bradley's No Safe Place book about the results of Baker?
Yeah, so I don't know Bradley's book in a really familiar way. I think I've like seen the cover. So Baker, the Applied Fisheries Lab scientists had a role to play in Baker, and you can see this this appears in some atomic stories. I think you can see this in J. Samuel Walker's book, Permissible Dose. I think he makes a reference to this. He was the historian for the Nuclear Regulatory Commission for some time, and wrote a number of really excellent books, insider perspective, but really thorough books. Allegedly, Warren, Warren was a colonel in the Manhattan Project. He went to Vice Admiral Blandy, who was in charge of Crossroads, And he said, look, it's unsafe for servicemen to be in the lagoon. And these ships that have gone into the lagoon with servicemen are now irradiated. They have radiation on their decks. They have radiation in their water pumps, in their filtration systems. We have to go. And so the apocryphal story is that there was meant to be a third shot during Operation Crossroads, but that Baker created such a radioactive burden that they left, and that the Applied Fisheries Laboratory contributed to this because Donaldson took a radio autograph. So he got a piece of coral and simply put it on an unexposed piece of film, and then the radiation exposes the film and gives you an outline of the coral. And allegedly Warren took one of these radio autographs to Blandy, the head person in charge, and said, this is what's on your ships. We have to leave now. I don't know if that's 100% confirmable. That's the apocryphal. So they had a sense of radiological danger. I mean, for the Hanford story, though, I'd point out that I do think that Warren was really actually concerned about the health of the enlisted people in the officer corps in the Army and Navy at Crossroads. That concern certainly didn't translate to people in Japan. And that concern didn't translate, I think, to Marshall Islanders. And I don't know that it translated to downwinders at Hanford either. So there was some disconnect there where, it's our job to keep servicemen, and again, men, because it's totally gendered spaces at this point. It's our job to keep servicemen safe, but wheat farmers on the Palouse, well, there's dilution. So there's a little bit of a disconnect there, I would say.
Yeah. Can you clarify if R stands for Roentgens or rad?
Yeah.
Are they the same thing? Are they different?
They are different. Here's a quick word on that. So Roentgens are a really early dose, and a really way of measuring radiation, a really bad way of measuring radiation. Because essentially what you do is you take a cubic square meter, and then you figure out what how voltage moves through that. I'm going to explain this wrong. It's about the electrical voltage in a squared area of air. REMs and RADs are about the ability of radiation to penetrate the body. So REM is Roentgen equivalent man. Again, super gendered. So REM tells you if you're exposed to this many Roentgens, it tells you what goes on in your body as though you were exposed to Roentgens, but inside your body. And there's going to be a health physicist who's going to rack me over the coals because I'm explaining this poorly. But the key thing to take away is that Roentgens are about just measuring outside in the environment, and REMs and RADs are about what's going on inside the organism. And trying to understand how radiation acts inside the organism. Because this was part of the problem. Obviously, your skin is an organ. It experiences radiation exposure differently than your liver or your lungs. What about your eyes that are covered sometimes by skin and not covered sometimes by skin? How did they experience radiation exposure? So these guys deal in Roentgens. When they go to Bikini and Eniwetak, they will deal in milliroentgens because radiation decays over time. So for example, a year after a bomb blast at Bikini, you might see exposures in milliroentgens that are still constant, but are very, very low level exposures. But Roentgens are different than RADs and REMs, is the short thing there.
Thank you. How did early research account for thermal hot versus radiation hot?
That's a great question. Oh boy, and also just looking at the comments, thank you, Arjun, for looking at the one Roentgen is about 0.9 rad. Like I said, I'm a historian. I'm terrible with numbers. So they did account for the heat. I should have said when we looked at the Quonset and all the troughs that there was one tank filled with hot reactor effluent and one tank where reactor effluent had gone through a cooling coil so that it was the ambient temperature of the river. And they did get somewhat different results from those. Ironically, fish are cold-blooded. And so if you increase their environmental heat, not to a lethal point, but if you increase the heat, they actually mature quicker. So there was a little bit of conversation about like, oh, dumping reactor effluent into the river is not a bad thing because salmon will actually mature more quickly if we can raise the temperature just a little bit and their metabolisms speed up. Of course, that didn't really come to pass ever. But yeah, they did run studies in the late 40s and in the 50s, certainly, on what the heat pollution was doing to the river. From especially once you had the B and the D and the DR and once you got all the reactors running at Hanford, that was that. So